welcome everyone to the openacc course. Thanks a lot for joining us today and spending your morning, afternoon, or maybe night with us. So we really appreciate it. My name is Julia Levitas. I'm a product manager at our Tesla group, and will help to kick off this second lecture of the course. If you missed the first lecture or the office hour, so not to worry. We do have all the recordings published and also Q&A transcribed on our openacc course page. To find this page, I posted the link in the chat window, and also you can just Google openacc course, and we will be the first page to show up in the search results. So let me start with some logistics. First of all the lines are muted just to make audio crisp for everyone and to have a really nice recording. So please submit your questions through a chat window on the left-hand side towards the bottom of the screen. We'll do our best to answer as many questions as we can today, and in case we won't get to every single one of them, we'll be covering the rest during the office hour next Tuesday on October 20th. Also, I guess that's it for the logistics. Now we're ready to start the actual lecture. So Jeff Larkin will be your instructor today. Most of you already know him from the first lecture, but for all newcomers, at NVIDIA, Jeff works on porting and optimizing HPC applications. He is also closely involved with the development of both openacc and OpenMP specifications. So Jeff, we're ready to start.
Thanks, Julia, and welcome everybody. This course, we're going to be focusing on profiling and parallelizing your codes with openacc. Just a reminder of the course syllabus for those of you who are just now joining us. We are in Lecture 2. The first lecture was a very high-level lecture showing everything that we plan to cover over the course of these presentations. And this week we'll be focusing strictly on the profiling and parallelizing steps and going into a lot more detail on those. And of course, next week, if you have any questions, come back and we'll discuss them there. So today, I want to give you a more detailed introduction to accelerated computing, GPU computing, and what I mean by those terms, and then go into the two steps of identifying where there's parallelism in your code, and then how to express that parallelism to the compiler using openacc. We'll be using a different code this week from the first lecture, and we'll be using the same code this week and in the lecture in 2 weeks. And of course, once again, there will be a homework that you can elect to do using our Quick Lab system. So getting started, let's talk about accelerated computing and what that means. So in the previous lecture, I showed you this slide and discussed how for most HP systems in particular, but also your laptops, your cell phones, most systems you'll buy these days have two distinct processors in them. There's the traditional CPU, which is really optimized for serial execution, for doing one long-running task very quickly. So there's usually some small number of cores. On a server class workstation today, you may have as many as 16 cores. On even a cell phone, you'll probably have 2, 4, or 8 cores. These cores generally run very quickly, and there's the way this architecture works is it's highly optimized using caches and fast clock speeds to work well on serial tasks. And then we have the GPU, which is really optimized for parallel tasks. So you can see here these blue boxes on the CPU that represent the CPU cores, and these green boxes on the GPU represent the GPU compute resources. There's many more compute resources on the GPU because it's really tuned for parallel tasks, for tasks where I have thousands or tens of thousands or hundreds of thousands of unique operations I can perform all in parallel and get high throughput. But let's focus in a little more on the specific strengths and weaknesses of both of these, because in fact when you're running your code in order to get the best possible performance, you're going to have some things that will run better on a CPU and some things that will run better on the GPU, and it's using them together that makes accelerated computing work. Starting with the CPU, CPUs tend to have a very large main memory. So for scientific computing in particular, we tend to have very large data sets, and CPUs excel at having space for these large data sets. On a server class workstation, you're looking at, say, 32 gigabytes and up for CPU main memory. They also have very fast clock speeds. So for the CPU cores, today you'll frequently find them upwards of 2 and 3 gigahertz, so very fast CPU clocks. And these CPU cores are what we call latency optimized. So if you're not familiar with the term latency, from the time that I request something from memory until the time I get that value back and I'm ready to compute on it, that is the latency. Latency to memory is I make a request to memory, and by the time it comes back, how much time it takes for it to come back and be ready for me to work on, that's latency. And for a CPU, CPUs have multiple levels of cache and have very large caches so that we don't have to make these trips to memory very often. So everything is optimized to reduce the latency by storing data in cache. Now, if we miss cache, it's a very expensive operation. Because the CPU cores operate at very high clock speed, if I miss my cache, there's going to be many clock cycles that pass waiting for data to come back from memory. So we really want things to live in the cache. And CPUs do a lot of things to ensure that your data will be in cache. We have cache prefetching. We have operations where we can operate out of order so that we can ensure that our data is in the cache and ready to go. You even have things like branch prediction to make sure that your CPU cores don't idle because we're waiting to figure out which direction we're going to take on an if statement. All of these things really revolve around making sure that the CPU remains busy and we optimize around the latency. This means that for some small number of tasks, usually revolving around the number of CPU cores we have, those operations can run very, very quickly. Now the weaknesses are, because we have such a large main memory, typically that means we have to buy lower bandwidth memory. So on most CPUs these days, you're looking at DDR3 or on the very newest architectures, DDR4 memory, which is at a lower bandwidth than GPU memory. As I already said, if you miss cache or if you mispredict a branch, this can be very costly. Lots and lots of CPU clock cycles will get wasted trying to catch up on that. And the last thing I'll call out, because particularly within HPC and within data centers, the cost of performance per power is very important. Compared to GPUs, CPUs have a lower performance per watt ratio. Now for GPUs, GPUs have a very high bandwidth main memory. So on current generation GPUs, which is the K40 and K80 products, we have a GDDR5 memory, very high bandwidth. But as I alluded to on the CPU, the trade-off is that you have a lower memory capacity. So on a K40 and a K80 both, you have 12 gigabytes of GPU memory per GPU. So much lower than most CPUs. We have significantly more of our silicon is dedicated to compute resources. That's what all these little green boxes are meant to signify. So what we have here is we have lots and lots of compute resources, and we want to keep them busy. And the way we do that is through parallelism. So I mentioned again that the latency is from the time I request from memory to the time I'm able to use the value read from memory. That is the latency. We, instead of having large caches and dedicating a lot of space to caches, we have built an architecture that tolerates the latency to memory. And we do that through parallelism. So if I have a thread that has made a request to memory and is waiting for the result to come back, what the hardware will do is swap in another thread and continue executing. And so our architecture is latency tolerant. We can deal with the fact that there is latency to memory because of parallelism. And as a result, we can dedicate space that would go to caches and put more compute resources. So we have a lot of compute cores on our hardware. This means we have very high throughput, and I'll discuss what I mean by throughput on the next slide. And the result is a very high performance per watt. So GPUs actually do use more power than a CPU, but we get more performance, and the result is higher performance per watt. Now there are some weaknesses to GPUs. First off, I already mentioned that the memory capacity compared to a CPU is lower, so 12 gigabytes compared to, in some cases, 32 or 64 or more gigabytes of main memory on many servers. But that's okay. We make up for that elsewhere. And lastly, a lower per thread performance. So if you look at any individual thread running on GPU, and again we have tens of thousands as opposed to say a dozen on a CPU, they will run at a slower speed, but we'll have more of them, and the result is higher throughput. So let's discuss speed versus throughput, because this may be a new idea for some of you. So let's think for a moment, if I want to get home from work, I want to leave my office and get to my house, the fastest way I can do that is probably to hop on a motorcycle. A motorcycle can go at a very high speed. It only has one seat, so there's absolutely no wasted space. I can even do a lot of tricks like weaving in between lanes, or possibly even running a red light if it's safe to do so, instead of waiting like the cars have to. So there's a lot that I can do to get home very, very quickly using a motorcycle. But the trade-off is that only I'm making that trip very fast. That if I had a second person or a third person or more, that the motorcycle is not a really practical way to do this. I can get one person home very quickly, but not more. If I have a lot of people to transport, a bus is a much better mechanism. So a bus may have to move a lot slower down the highway, and it certainly can't weave in and out of lanes like a motorcycle could, but I'm transporting, say, 200 people on a bus. Well, if I can get one person home in a half an hour on a motorcycle, then my throughput is one half of a person, in a half hour, 2 people per hour. So I can transport 2 people per hour using a motorcycle. If I'm driving the bus, for instance, on the same route, and even if it takes me a full hour to make that route, but I'm transporting 200 people, well then I've transported 200. My throughput is 200 people per hour versus 2 people per hour. So you can see I get much higher throughput even though I'm driving more slowly on the bus, because I can move more people at once. And this is a similar analogy with CPUs and GPUs. CPU cores do move much faster, and so if you have an operation that only really relies on how fast this one task performs, then a CPU core will do it faster. However, if I have a very large matrix where I need to calculate the same operation on every single matrix cell, then using a GPU and getting high throughput will get me better results. And for most scientific applications, we really truly have a busload of data that we need to churn through, and so a GPU does a much better job. So which of these approaches is better depends on your needs. But usually in scientific and high-performance computing, we have a lot of data that needs to be operated on, so a high throughput processor like a GPU will do better. So let's look at what an accelerator node looks like. We have said many times that there's a CPU and a GPU. The CPU has its own distinct memory, and this is a large memory that is relatively slower, and the GPU has its own memory that's relatively smaller but very fast. And the CPU and the GPU are connected usually via a PCI Express bus. Now, if I start my operation on a CPU, and we always begin execution on the CPU, then I need to offload not just my execution, but my data to the GPU. So if I'm calculating the sum of 2 arrays, I need to copy both of those arrays to the GPU before it can compute. And then I need to copy the results back to the CPU. And all of that is done via the PCI Express bus. And the bandwidth of the PCI Express bus, how much data we can copy across that bus, is much lower than that of the main memories. So we want to do that as rarely as possible. What we want to do is start on the CPU, put as much data as we need on the GPU, leave it there as long as possible, and then copy it back. And this we saw in the first lab that we needed to optimize our data motion to reduce how often we were making that trip between the GPU and the CPU. This turns out to be a very important aspect of accelerated computing. Now, optimizing these copies is something that we're actually going to discuss in the third lecture. We got a preview of it in the first lecture, but we're going to discuss it in detail in the third lecture. I'm going to do a little trick to make it possible for us to really ignore that step for another week. I'm going to be using something that's supported on all modern NVIDIA GPUs called CUDA Unified Memory. Now, this is something that we introduced in CUDA 6. It's something you may have actually heard also referred to as managed memory. So the picture I showed you a moment ago is true for most systems without unified memory. We have a CPU and a GPU and two distinct memories. Anytime that I need to move data between them, I have to be very explicit. I allocate memory on the GPU, I copy from the CPU to the GPU, I copy it back. I have to be very explicit and manage two copies of my data. Unified memory, I have one pointer that is visible from both locations. That allows me to push away the thought of how to manage my data movement and let the runtime handle that for me. So this is what we're going to do for this week's lecture and this week's lab, is I'm going to use CUDA Unified Memory to manage all of my data motion for me, and then in the next lecture we will make it more explicit. And it turns out that for this code and for many codes, the performance between explicitly managing your memory and allowing the runtime, the CUDA runtime to manage your memory is very similar. And so that's useful. Of course, the trade-off is the code you write will only run on NVIDIA GPUs. We want to go ahead and make our data in motion explicit at a later time. Those of you who came to the first lecture will recognize this graph. These are the 4 steps, or the 4-step cycle that I taught you about accelerating your code with openacc. We start off by profiling the code to identify where there's parallelism that we want to exploit. We next express the parallelism in our code using openacc. We inform the compiler where the parallelism is and allow it to build it for the GPU. Next step is to express the data movement. That's what I was just talking about, trying to ensure that our data lives on the GPU as long as possible. And then lastly, there are some optimizations we may be able to perform to get even better performance. And for this lecture, we're only going to focus on the first 2. Come back in the lecture in 2 weeks, and we'll go into more detail on the following 2. So for this lecture and the next, we're going to provide you with a code. This code solves what's known as the conjugate gradient problem. And I'm not going to go into any detail about that method, but I will point you to Wikipedia has a great article to discuss this. You don't necessarily need to know the math behind it to do this lab. We've provided the code for you. We've provided both C and Fortran versions of this code. So when you're doing the lab, if you're more comfortable in Fortran, it's available for you. If you're more comfortable in C or C++, that's available to you. I'm only going to show C in these lectures because that's where most of the interest is. And we'll use this same code for the next 2 lectures, the next 2 lab. So you can actually, if you want to do the code using the Quick Lab system, we've made that available to you. Or if you want to see the code yourself, I've placed it up on GitHub for you. And here's the link to go back to later. So step 1, let's talk about identifying the parallelism in our code. And there's a lot of tools that you can use to do this. Some of you may be familiar with tools such as Tau or Vampire or HPC Toolkit or Cray Performance Tools or gprof or pgprof. There's lots and lots of tools. Because I want to teach something that I know will be available to you on any machine, I'm going to show you 2 tools that should be available anywhere. First is the NVIDIA Visual Profiler. So if you've downloaded the openacc toolkit, or if you've downloaded the CUDA toolkit, this is available to you. Traditionally, we've used NVProf to look at the performance on the GPU. However, with CUDA 7.5 and with the openacc toolkit, we've added support for CPU profiling. To be specific, what we do is we do CPU sampling. So on a very regular basis, every fraction of a second, we are looking at what the CPU is doing and recording that. And of course, we can also do GPU profiling, so get a high-level statistics about where our time is being spent. We can also gather a timeline, and I'll show you what a timeline looks like, so you can see where your computation occurs, where your data transfers occur, and things like that. And then we can also gather some metrics for offline analysis and get really good detail about how our code is performing. And then it will also show us some information about the unified memory and how it performs. This is the tool, incidentally, that we use behind the scenes in our visual profiler. So this is a very well-tested and well-supported tool. So for our code, I've gone ahead and skipped the step of building it. There is a makefile provided for you, so there's instructions in the lab of how to build it. But I'm going to use the NVProf tool first to gather the profile. So CG at the end here is the name of our executable. Go ahead and highlight this. That's the name of our executable. And then this nvprof command is what is actually going to instrument the code. So the flag that I'm using is CPU profiling on, and this CPU profiling mode is just, I prefer the top-down view. It's simply a change in the way the data is shown to you. All of this is available. If you type nvprof --help, it'll give you about what these flags do. So I run it, and you can see this is this first part is the normal program output, and the stuff down the bottom is what nvprof adds. And what we see is, of course, we're spending most of our time in main. That's what you would expect. And then there are 3 routines, 1, 2, 3, that really stand out as the most important parts of our code. There's one called matvec, that is a matrix vector multiplication. There's one called waxb and one called dot. And these are the 3 routines that during the lab we're going to speed up. This last one here, allocate 3D Poisson matrix, is an initialization routine, so we're going to ignore it because it's not really important. So I see here that these are the 3 most important routines. Now I do want to show you another tool that's also widely available. So again, if you've downloaded either the openacc toolkit or the CUDA toolkit, you have nvprof available to you. If you've downloaded GCC at any time, so which the GNU compiler collection, you will have this other tool, which is gprof. And again, it's a command line profiler that allows you to get information. The way you use it is you add this -pg compiler flag at compilation. And that's true for both the Portland Group compiler, PGI, and for GCC. You run the executable, and it's going to create this extra file here called gmon.out. And we use the gprof to analyze it. And the output will look something like this. It'll actually be a lot longer than this. I've really pulled out the important part. And what we see again is our 3 most important routines here, matvec, waxb, and dot. So you can use whatever tool you're most comfortable with to get this information, but these are 2 tools that I know will be available to you. And there's more information in the lab about how to use them to gather this information. Now, so once I know where I should be looking, I need to look at these 3 routines. I should start getting some data about those routines in particular. So to do that, I'm going to use compiler feedback. Every compiler that I'm aware of has some form of compiler feedback to tell you what it is doing to the code, so how it interprets the code and what optimizations it performs. On the PGI compiler, this is enabled using the -minfo flag, and there's some important ones here that important options I want to highlight. So -minfo equals Excel. This is a flag that says, when I'm building with openacc, tell me what you're doing with my code. minfo equals all will print out nearly everything. So it'll print out the stuff from Excel. It will print out whether or not it unrolled your loop, or whether or not it used SSE or AVX instructions on a modern CPU, what optimizations it could do. Another really useful one that's not included in all, this is why I say it's nearly all compiler output, is intensity. Intensity will tell you how much work your loops do. I'll explain that in about 2 slides. And then CCFF is one that's sometimes useful when you have tools that understand it. It will put all this information into your executable so that the tools will see that information. So it's sometimes useful to have as well. So what I've done here is I've built my code. This should the PGC++ is the compiler, and -fast is the optimization. And you can see I've added my -minfo flag because I want to know what the compiler is doing. And I've shortened the output to fit here, but in the waxb routine, which is one we saw was important, we can see, well, this came from vector functions.h. You could see some optimizations it did. So may or may not make sense depending on how much experience you have with compiler optimizations. And another important one here is the intensity. So it tells me that for the loop at line 24, which it turns out to be the main Waxby loop. If you follow this down the indentation here, I have a computational intensity of 1. And matvec also, it tells me, I came from matrix functions.h, so now I know where to look for this function. There's a loop at line 18, and it has an intensity of 1. So why is computational intensity important? Computational intensity is the measure of how much work you're doing compared to how many memory operations you perform. So a memory operation is a load of a value from memory or a store of a value to memory. So if I want to add things together, if I want to add A and B together and store into C, I need to load A. That's one memory operation. I need to load B. That's another memory operation. I need to store C. That's another memory operation. But I have one addition operation. So that's how computational intensity works. So compute operations, add, multiply, subtract, divide, things like that, over memory operations, loads and stores. A high computational intensity is often an indication that something would run well on a GPU. That's because the amount of time we spend copying data to the GPU is going to be offset by how much work we've done. And so typically if you see a computational intensity of 1 or greater, that's frequently a clue that this is something that you might want to move to the GPU. So going back to our compiler output, you can see here that both of these main routines, these major routines, have loops with computational intensity of 1. So this is something that we might want to consider moving to the GPU. So once we've determined where there are loops we want to the GPU, move to the GPU, we need to take a look and try to understand whether or not our code is parallel. If we want to run it on a GPU and really take advantage of the GPU's strength, we need to run in parallel. So here is the main loop that we've been referring to. This is that loop at line, I believe it was 18 of matvec. And what we see here is it's a nested for loop. What we've done inside this loop is we're doing a sparse matrix vector multiplication. So we have a vector, a matrix that we're storing in something known as compressed sparse row format, which basically means we store the important parts of our array and we throw away the rest. So this section here is finding the important parts of our for each row, and then this next part is actually performing the math on those parts. Now I've highlighted here all of the times that we are either reading from an array or writing to an array. And I want to look at these carefully and make sure I know, is there any time where one loop iteration affects the results of another loop operation? And what we see here is I'm only reading from the calls array in one place. The same with A coefs, same with X coefs. The only place I'm writing is down here to Y coefs. So there's actually no place here where I would read from and write to the same array in within the same loop. If I look more closely, there's no places here where iteration 1 would affect iteration 2 of any of these loops, for instance. So what we are looking for is data dependencies. Any time where one loop iteration would affect another loop iteration, that's known as a data dependency. And staring at this and looking at this, I don't see any places where that occurs. So there's no data dependencies within these loops. Now I want to call out this sum operation because some of you might look at that and wonder whether that is a data dependency because every iteration of this loop is storing into the same variable. It's storing into sum. This is what's known as a reduction operation. So the way to think about this is for every single iteration of this innermost J loop, I am calculating A coef times X coef. I'm calculating a unique value of that. And I'm storing those into sum. So what I'm doing is I'm taking many values of this operation and I'm reducing them down to 1. And the way I'm reducing them is using the addition operator. So this is known as a reduction. Now, if you're familiar with floating point math, the order of operations may change. So that does mean that for floating point math, you may see a few of the least significant bits change because we're not running in the same order that we do when we run it serially. but we will still get essentially the same answer. So this is a reduction, and reductions can be done in parallel. So this is not going to prevent us from parallelizing our code. Here are our other two routines, just briefly showing them here. And in both cases, once again, we have loops that are fairly simple to parallelize. The first one from wax speed has no data dependencies. The second one from dot has, again, no data dependencies, but it does have a reduction. So we do know that all three of the main loops in this code can be parallelized. Now we need to tell that to the compiler. Move on to the expressing parallelism step. So in the first lecture, I talked a little bit, very, very briefly, about the openacc kernels directive, and I said that this identifies a region of code that can turn loops into kernels. And if you're not familiar with GPU programming at all, that statement might not have made a lot of sense. So I want to go into a lot more detail here to explain to you what I mean by loops and kernels. Before I do that, I will show the syntax. So we have a region. In this case, I'm writing in C, so I have some curly braces to identify the region, here and here. And I'm applying the kernels construct to that region. And the kernels, the compiler is going to look at this. It's going to see two different loops, and it's going to generate what we will call two kernels. Let's not get hung up on that terminology just yet. I'll show in a moment what that means. Now, it does look a little different in Fortran, so I want to highlight this for the Fortran programmers. Here we have a starting ACC kernels and an ending ACC end kernels. That's because until recently in Fortran, we didn't have something similar to the curly braces to show blocks. It's also worth mentioning that if you're a Fortran programmer, ACC kernels will parallelize array syntax. So if you have array syntax in your code, you can still use ACC. So let's talk about loops and kernels. So when most of us learn programming, one of the first things we learn from the very beginning is how to write a loop. So I have here three arrays, A, B, and C. And I want to add A and B together and store into C for every single array element. So naturally, I would write a loop that starts at 0 and goes to the last element and adds them together in order. So what I get is one really long running thread where we'll calculate every single element of this array from 0 to 16,383 in order. So this is a traditional loop. All of us are probably familiar with this if you've done any programming at all. What if instead of writing a loop that visited every single element, instead I wrote a function that only calculated one element? What would that buy me? First, it would look like this thing on the right. So here I've called it loop body because it very closely corresponds with the middle of my loop here. I take in A, B, and C and my index, so what value I want to calculate. And I calculate only that value. This is what I would call a kernel. Now, on the surface, this might not look like it's bought me anything. On the surface, you might think, okay, well, I'm going to call it with 0, and I'm only going to calculate 0. So if I want to calculate every single element, I'm probably still going to stick it in a loop. And that might be true on a CPU architecture, but on a more parallel architecture, there's something really powerful about having a kernel. And what I know here about this kernel is, if I look at where I'm accessing memory, every single call to this function is fully independent of every other one. I'm taking in I, and for a value of 0, I'm only calculating 0. And for a value of 1, I'm only calculating 1. So every function call is independent. So I can run them in order, I can run them backwards, I can run them in a random order, or I can run them in parallel. Because I know there's no side effects here, and I'm only calculating within this function and not affecting any other call to this function, I can run them in parallel. So this is really powerful on a GPU. And in fact, in an explicit programming model like CUDA, what you do is you write kernels. In openacc, instead, you tell the compiler, hey, I have this loop, and I want you to turn it into that kernel. And by doing so, it can run in parallel on So let's look at this directive one more time. The kernel's directive identifies a region of code where I think the compiler will turn loops into for me. So here is the exact same code I had on the previous slide, and you can see all I had to do is wrap it with an ACC kernel's. There's a lot of stuff going on behind the scenes when I do this. First, the compiler is going to analyze this code for me and decide whether it's parallel. It will look at this code, look at all of the data dependencies, are there data dependencies, and will determine whether or not it can parallelize this. It will also look at it and figure out what data needs to be moved to the GPU. It's going to figure out that A and B need to be copied over to the GPU before I can perform my calculation. And after I'm done, I need to copy C back to the CPU. All of that is managed for me by this directive. And of course, lastly, it will generate my kernel, and it will figure out how to run that on the GPU. So all I have to do is point it to where the parallelism is. In this case, point it to this loop. That's how the kernel's directive works. So let's apply it to our code. And I'm going to show you this is the same code that you'll be doing in the lab. So I'm showing you the answer to one of the three functions, in this case, matvec. Here again is my matvec loops, and all I've done is wrap them with an ACC kernel's region. There's really not much else to this function here. And all I've done is added this. So I've told the compiler, I know there are loops here that I want you to analyze. And I'm not going to worry about what data is going to be used. I'm going to let the compiler do it for me. So next, I need to build the code. As you saw in the first lecture and lab, we're going to use the -TA flag from PGI. This is the target accelerator. We're going to tell it to target a Tesla, an NVIDIA Tesla GPU. And we're going to tell it to use CUDA managed memory. And again, we're doing this right now so we can ignore the memory movement. And then in the next lecture, we will remove that and make our motion explicit. So I'll build the code. Again, I've added minfo to tell me what's going on, and TA equals Tesla:managed to tell it to build openacc. And right away, you see the importance of turning on the compiler feedback. Because although I've looked at that code and I've assured myself that my code is parallel, the compiler thinks there are some loop dependencies. The loop at line 16, it believes there are dependencies in my loop. Now, it did still generate an accelerator kernel, but it's not going to get as much parallelism as I hoped because of these dependencies. So what's going on here? Because I looked at the code and decided there wasn't anything to block parallelism, but the compiler disagreed with me. Well, this turns out to be a really common problem in C and C++. Now, the Fortran programmers are really lucky in this regard, but C and C++, this is a really common problem. This is something known as false aliasing. So if you're not familiar with the term aliasing, aliasing means I have two pointers that might point to the same memory. Now, for most of the time, when we allocate an array in C or C++, we allocate an array to a pointer, we allocate a different array to another pointer, and we never actually overlap those pointers. The problem is that when I pass those arrays into a function, the compiler has no way of knowing that. And so a compiler, not wanting to give you wrong answers, is always going to assume the worst. So it assumes that there's some chance that they will overlap, and it's going to not parallelize as a result. Now, there's a few easy fixes to this, and we're going to apply them to this code. Now, as I said, Fortran arrays can never be aliased, so they don't have this problem in Fortran, but in C and C++, this is a really common problem, and it's not just an openacc problem. Some of you may find that you're not taking advantage of, say, the SSE or AVX instructions on your CPUs because the compiler can't optimize your loops effectively. So one way to fix this is using the restrict keyword. This was added in C99, and it's technically a C keyword, but I've never come across a C++ compiler that won't respect it. So this is my preferred approach. This is a promise that I give the compiler that this pointer does not overlap with any other pointer. You can get a lot more information about restrict on Wikipedia. There's a link down the bottom here. But what you'll do is you'll apply this to your pointer, say float star restrict and then pointer. And this will say for as long as this pointer is around, it will not overlap with any others. Now, I'm making this promise to the compiler. If I break that promise, it's my fault. But this is more than 9 times out of 10, this is what you've implied with your arrays. This is what you intended with your arrays. So it's any time that you're using arrays within C, you might want to consider using the restrict keyword because it's not unique to openacc. Optimizations in general will require, parallel optimizations will require this knowledge. So that's how that's used. Now, in cases where that's not sufficient, openacc also has a loop clause called independent. And so we already saw the loop directive in the previous lecture. It provides information about the next loop. And the independent clause informs the compiler that all iterations of this loop are independent with respect to each other. So this tells the compiler, don't bother analyzing this loop. I'm telling you it's independent. And again, if I tell the compiler that and I'm wrong, then it's on me. But here's how I've applied this. So in ACC kernels region, and I've told the compiler that each of these loops here are independent loops. So it doesn't need to analyze them for me. So that's one additional approach that you can take. Now, I personally like to take the restrict approach because it's portable, it's built into the language, and because it could enable my code to run faster on the CPU as well. So here are all of my array declarations inside of the matvec, and you can see I've added the restrict keyword to each of them. So that's what I would suggest that you do in the lab. And I guarantee you that some of you who are running the C or C++ lab will miss this part, and you'll not see as good a performance. And again, the output to look for, I'll go back here, is if you see something about a complex loop carry dependence, that is a sign, at least within this code, that you need to add the restrict keyword to tell the compiler that there's no aliasing. All right, so let me rebuild the code now with that fix, and you can see things have changed. Now it's telling me, hey, that loop that you told me about, both of these loops are parallelizable. And so it's going to generate a parallel kernel for me. Now let's look at the performance. And just like last week, we see our performance actually slowed down. And I want to point this out to you because it's important to remember that as you're doing this, for the first couple steps, you may see a slowdown because we haven't dealt with the data motion yet. And even with unified memory, what's going to happen is that I'm going to run matvec on the GPU, but then I need to copy the results back for the other two routines. So until we get everything on the GPU, we will see a slowdown. Now I want to show you a tool called Visual Profiler. Visual Profiler comes with the CUDA toolkit, and it's available on the QuickLab machines. And so once you've launched Visual Toolkit, there's instructions on how to do that in the lab instructions. I chose File, New Session, and I ran my executable. And here's what it looks like. And at this step, you see I have one kernel running. That's my matvec kernel. And you can see it's running a whole bunch of times. And then up here, it has a unified memory section. So that's telling me when I'm migrating my data from the host to the device, so from CPU to GPU, and from the device to the host, from GPU to CPU. And what we see is before and after every single call to matvec, I'm having to migrate my data back and forth. So I'm spending a significant portion of my time migrating data. And this is what is going to be your assignment to fix this week, is to accelerate the rest of this code so that you get a speed up. And here's what the final result is on a modern Haswell and K40 machine, so K40 being an NVIDIA Tesla K40 GPU. And you can see we, after step one, after accelerating just one kernel, we slowed down. But once we had everything on the device, so I didn't have to copy the data back and forth, I see a speed up. Now, on the QuickLab machines, you will not see quite as large a speed up. You'll see something in the ballpark of 10 to 15%, and that's simply because the GPUs are much smaller than the one I'm running the test on here. This is a top-of-our-line GPU, and those are much smaller GPUs that are intended for the cloud. So you won't see quite as much a speed up, but you will see a speed up. And we'll do some further optimizations next week. Now, I need to present to you a second approach to accelerating using openacc. So kernels is one way where I can ask the compiler to do all of the hard work for me and look at my code and ensure that it can be parallelized and parallelize it for me. Now, for some of you who already have experience with parallel programming, you might already know that your loop is parallel. And you might just want to go ahead and tell the compiler, don't worry about the analysis. I know that it's parallel. This is particularly true if you're coming from OpenMP and you already have parallel loops in your code. You may already know that these can be parallelized, and you want to skip that step. So the parallel loop directive is really two directives. It's the parallel, which says, here is a block of code that I want you to run in parallel, and loop says, this is the loop that I want you to run in parallel. And so usually you put them together like this, ACC parallel loop. And it's going to generate this for me. Now I mentioned the independent clause, and on parallel loops, independent is implied. So what I'm really saying here is this loop is independent, and I want you to run it in parallel. So I'm taking all of the burden of analysis upon myself and just asking the compiler to parallelize it. And that's really the fundamental difference here, is I'm taking control and taking responsibility. And because of that, if there's anything that I need to inform the compiler about in order to make the code safe to parallelize, well, I have to take responsibility of that. And two such things are private variables. So if there is some variable in my code that every single loop iteration stores to, then we're going to need a separate private copy of each of those. Similarly, I showed you a reduction earlier. Well, if there's a reduction in my code, I need to tell the compiler that if I'm using parallel loop. And so I would specify that this is a reduction. If you're coming from OpenMP, both of those behave in a very similar way and should be familiar to you. If you're starting off and you're using the kernel's construct, then you won't need to worry about these right now. So let's see what the code looks like so you can see the difference. Now, instead of ACC kernels, I've said ACC parallel loop on this top outermost loop. And on this innermost loop, I've specified, hey, there's a reduction here. And so I've done the analysis. The compiler doesn't have to, and it will generate the kernel. And you can see from the compiler output that it does roughly the same thing, and you will get roughly the same performance. In this particular lab, what you'll find is that the parallel version at the end of lab 2 will run a little slower than the kernels, and then at the end of lab 3 they'll both run at nearly identical speeds, actually basically identical speeds. So one question that comes up a lot and is a major point of fusion is, why does openacc have two different ways to do the same thing? They're very similar. Parallel loop is completely the programmer's responsibility. So I am taking it upon myself to say, this is something I want parallelized, and here's how to parallelize it. So it's very good if you already have done an analysis in your code. It's also very good if I've tried ACC kernels and the compiler is still missing something. So it's a very straightforward path from OpenMP. Kernels is, excuse me, taking the responsibility and handing it to the compiler. The compiler fully does the analysis for you. It parallelizes what it believes is safe. It also allows you to cover a very large area of code. So if I have one function that has lots and lots of loops in it, I can put a kernel's region around all of them, and rather than having to go to every single loop independently. And lastly, it does give the compiler a little extra room for optimization. There are a few optimizations the compiler might do on kernels that it might not do on parallel loop. So that's one other reason. But at the end of the day, both of these approaches are valid, and both can perform very well. And the more information you give the compiler, generally these will perform equally well. So it comes down to whose responsibility do you want it to be, the compiler's or the programmer's. Okay, so that's the end of that step. Let's review what we've discussed today. I've shown you a few tools, two different tools NVProf and GProf that will allow you to profile a code and identify where there are important functions in your code, and then how to look at those loops and make sure there's nothing there that will block parallelism. So there's no data dependencies, how to find a reduction, and things like that. I've shown you two different approaches to express the parallelism in your code. For most of you, the kernel's approach is probably the simpler approach, and it's probably the approach you'll want to take. But for the more experienced parallel programmers, there's also the parallel loop directive, which allows you to take control and give the compiler the information to parallelize the code. Lastly, I've shown you how to build and run the code using openacc, and then how to use the NVIDIA Visual Profiler to get a profile. And there's more instructions on exactly how to do that. I've only really showed you the results, but there's instructions in the lab of how to get that profile. So let's finish up by talking about our next steps. Of course, this is only half the story, so I really want you to come back in 2 weeks on October 29th, and what we'll do is we're going to take away unified memory and be really explicit with our data movement. And lastly, there are some optimizations we can make to this code that will actually, it turns out, get about a 2x performance improvement through these optimizations. So I want to show you how to apply those optimizations. So please come back and see the rest of this story. Lastly, is your homework. And the homework is to go through this exact code and run through these steps. So if you go to this link, this lab is free and will remain free for the remainder of this course. You will build and profile the example code, and again, it's in C or in Fortran. And you'll then go through each of the 3 routines and accelerate the code, and you can use either kernels or parallel loop to do that. And I encourage you that every step of the way to regather your profile information, run through Visual Profiler, and look at and see the difference and what the changes you made and how they affect the code. Really interesting to watch. As you add one function, parallelize one function, the data movement goes up. And as you add another function, your data movement slowly goes down until the point that all of your computation is on the GPU, and then you see everything stays there. Really interesting to watch step by step. I do need to emphasize, I showed you a pretty substantial performance improvement on a Haswell and K40 machine. On the GPUs that we have up in the cloud are much smaller GPUs, so you only see about a 10 or 15% improvement. So don't get discouraged if that's all you see. That is expected. And in Lab 3, we'll improve upon this. We'll get it roughly a 2x improvement at the end of Lab 3. So do come back for that. As a reminder, next week is another office hours session. So if you have questions from this week, if something confused you and you want us to go into more detail, or if you try the homework and get stuck, come back next week and talk to us, and we'll go through that with you. And if you absolutely can't wait till then, go to Stack Overflow and ask your question with the openacc tag, and there's a bunch of us who will read that. And then to close here before I go into the Q&A, as I said, we're in this second block of this code. October 15th today is this lecture, and on next Tuesday is the office hours that go with this lecture. And then come back in 2 weeks on October 29th for the rest of this case study. So with that, what I'm going to do is I'm going to go over to the questions that are asked, and I'll try to answer as many as I can. And those I don't get to, we'll try to answer next Tuesday. One question was, what about integrated GPUs where they share, the GPU and the CPU share memory? OpenACC, the way it is written, allows for either distinct or shared memory devices. So you can still use OpenACC on a device where they share. In those cases, you won't need to use the data directives that we'll talk about in 2 weeks. But if you want your code to be able to run on both a distinct and a shared system, that you'll need to do that. So it definitely will work. And in using unified memory this week, what we've done is something that is very similar to an integrated type approach. So it should work very similarly. Here, there's another question about the GPU RAM. So let me go back to those slides real quick. So does the RAM on the GPU refer to GDDR memory? And yes, it does. So So this is what we refer to as the frame buffer memory on the GPU. So the GPU has, on CPUs, we usually have DDR3 or DDR4 main memory. These are the little sticks that you can stick in there to upgrade your memory. And then on GPUs, we use a GDDR5 memory, which is a much higher bandwidth memory. But because it's higher bandwidth, it's more expensive, and that means we tend to ship less on the GPU. Oh, here that the audio got cut a little bit. What does aliasing mean for a pointer? So aliasing takes place when two pointers point to the same memory. So if you have, say, a pointer pointing at the beginning of an array and a pointer pointing to the middle of the array, those two pointers are aliased. Now, most of the time, we're not doing that. The problem occurs when the compiler doesn't know that we're not doing that. So if you think about a function, and I'm passing in two arrays into a function that I want to sum together, A and B. Now, I know that I'm passing in the A array and the B array, and those are two distinct arrays. But to the compiler, when I'm inside of that function, all it knows is there are two pointers. And it has no way of knowing that you didn't pass A and A into that function, or B and B. And so aliasing would occur if I passed A and said to add them together. And so by using the restrict keyword, I inform the compiler that these are always going to be two different arrays, A and B, and I'm never going to pass the same array into that function. So that's why the restrict keyword is important, and that's why we avoid aliasing. Aliasing, again, is two pointers referring to the same memory. There's a question here: does the CPU profiling from NVProf work with openmp? And I'm pretty sure the answer is yes. However, I need to check on that, and I'll try to follow up on the office hours next week to make sure that that it works correctly with host threaded code. A question here: can unified memory be larger than GPU memory? And that's a very important question. So the way unified memory is implemented on today's hardware, it cannot. So if I have a unified memory space, I'm limited to as much memory as will fit on my GPU. And to be more specific, if I use the PGI TA Tesla :manage flag like we're using here, then all of the memory used by my program has to fit within GPU memory. That is something that is due to the inability of today's GPUs to be able to page fault. So yes, you are limited by how much space is available on the GPU. And Julie, I think that's probably all the time we have, and we have a lot of questions here that we'll try to answer before the office hours next week.
Okay, Jeff, if you have a couple more minutes, we probably can take a couple more questions.
Okay.
If you don't mind, because there are a lot of them answered.
So there's a question here, and this is clearly coming from someone with some CUDA programming experience, is how does openacc work with CUDA pinned memory? So for those of you who have not programmed in CUDA, pinned memory is a type of memory that I tell the CUDA runtime about. It does some tricks behind the scenes, and as a result, it can transfer at roughly twice the speed across the PCI Express bus. And it's also needed anytime I want to operate asynchronously between the CPU and the GPU. So openacc does work with pinned memory, and in fact, anytime that you do asynchronous programming with openacc, the compiler has to pin the memory behind the scenes. So you can pin things. Additionally, if you know that you want to pin all of your memory, rather than using the CUDA function calls to do so, a PGI compiler will allow you to say TA Tesla pinned instead of managed, and it will pin all of your memory to ensure you get the very fast PCI bus transfers. So pinned memory is still beneficial with openacc, and there are ways, like I said, to use it effectively. A question here: which approach is safe, kernel-based or parallel loop-based? And if you are a brand new parallel programmer, the kernel's approach is always going to be the safest, because the compiler is going to look at your code. It's going to decide whether it has enough information to decide whether it is safe to parallelize. And it will only parallelize if it's totally convinced it's safe to do so. And that's actually why we saw on the one slide that until I added the restrict keyword, if I could find that slide, the compiler explicitly did not parallelize my code. I parallelized part of my code, but not all of it, because it was not convinced it was safe to do so. And so that's why I went back and added the restrict keyword. So kernels will always be the safer approach to use if you're not confident about the parallelism in your code. If you're confident that the code you have is parallel, can be run in parallel, this loop absolutely has no parallelism blockers, then both are equally safe to use. But it's at that point your responsibility to ensure that. So kernels is the safer approach if you're not experienced with parallel programming. A recent question here: what does openacc do when a loop contains calls to a class function? I'm just going to expand that out to functions in general. So in openacc, because you may have loops outside of your function and inside of your function, one thing that's really important is that you inform the compiler of any parallelism in your functions. So all function calls called within openacc regions get decorated with something called the ACC routine pragma. Now, this is something that we're going to show in the fourth lecture. We'll have a code example there of how to use it. But if you need to know about it ahead of time, if you'll check out the openacc programming guide that's either in the openacc toolkit or available on openacc.org, there's examples of how to use the routine directive so that you can make function calls within your openacc loop. If I can find
okay, let's take one more and then we will close after it. Mm-hmm.
Yes, one last question. Where exactly does unified memory exist, on the CPU or GPU? And this is such an interesting question. So the answer is both. So with unified memory, I have a single pointer address that the program will access. And on modern machines, that is a virtual address. And so that virtual address can point to any sort of physical page. And so what happens is, behind the scenes, the CUDA runtime will change the physical address behind that virtual address. So when I'm running on the GPU, that pointer will exist on the GPU. And when I'm running on the CPU, that will exist on the CPU. Now, one very important caveat there is that I can't access the pointer from both at the same time. So it's very important, and the openacc runtime handles this for you, it's very important that after I'm done running on the GPU that I synchronize to make sure that any changes I made on the GPU come back to the CPU. It's all handled invisibly for you by openacc. So where does it exist? It exists in both. It's a virtual address that, depending on where you're accessing your data, it will physically exist either on the CPU or the GPU. So I think we'll push off the rest of these questions to the Q&A. I hope people who ask them will come back and come back to the office hours, and we'll try to answer as many as possible.
Yeah, thanks a lot, Jeff. There is really a lot of questions. We did answer a few of them while Jeff was talking, but we didn't cover all of them. So please join the office hour. The next office hour will be on Tuesday at 9 o'clock Pacific time. And we'll have the whole hour just for questions, so we'll totally will be able to answer those that you submitted today and whatever new you have. We'll do our best to answer as well. And there are a lot of questions about where you can find the recording, and there are Q&A questions from today and from the previous sessions. So if you just Google openacc course, you will find the openacc course page where we post all the recordings. And today's recording will be posted there as well. First, we'll put their slides and the video recording, and later in a couple of days, we'll also transcribe all the Q&A and put there as well. So please keep an eye on this page, and you'll find all you need over there. That's pretty much it. Don't forget to join the office hour next week. We're looking forward to see you, and thanks a lot for joining today. Thank you.